So last time we looked at some universal statements, and for those statements we were saying whether they're true or whether they're false. All squares are white, is it true or false? All white shapes are squares, is it true or false? So how do we go about proving that a universal statement is false in general? Well, false is the easier part of it. All we need to do is to get one counterexample. So let's look at some example. Imagine that somebody says, as people sometimes do for I don't know why a reason, all girls hate math. What am I going to reply to that? How do I prove them wrong? Well, it's actually easy because it's enough for me to say, well, I don't hate math. And here is one counterexample, the only one you need that proves you wrong. Or say somebody says, everybody in O'Brien's family is tall. And it's enough for you to say, well, Jenny is short and she is O'Brien. You found a counterexample, and that's Jenny. Another one which, well, it feels like it's true, it's foggy all the time, every day in St. John's. Well, sometimes it's not foggy. Like today is just snowing. So here are our counterexamples. For the first one, I am the counterexample. For the second one, Jenny is. And for the third one, it's today. So a counterexample is an element of the domain on which the formula is defined, of the universal quantifier, for which the formula is false. And there can be more than one, but one is enough. So in general, as you know, when a statement is false, that means that its negation is true. And nothing stops us from taking a negation of a predicate logic formula the same way as we did it for propositional logic formula. We just define it to be something that's true whenever the original thing is false, and false whenever the original thing is true. So, but how do we actually write it? So let's look a little bit more closer at those responses. So again, suppose somebody says all girls hate math. How would you say, no, the opposite is true? So what's the opposite? If you say all girls love math, well, she may say, no, I'm the counterexample. You're in the wrong now. But you don't have to say that. It's enough that some girls don't hate math and say, well, I'm one of those girls who doesn't. So an opposite of all is some. Similarly, if you want to say that it's not that everybody in O'Brien family is tall, it's enough to find someone, say Jenny, who is O'Brien and short. Foggy all the time? Well, sometimes, like today or maybe some nice day in July, it's not foggy. So here is a general rule. If you want to say that all is not true, that means that for some, the not of that formula is true. All girls hate math, some girls do not hate math. So you switch the quantifier and the not, and the quantifier flips. All becomes some. And now we actually have a symbol for that sum, and it's called the existential quantifier. So just to reiterate, so far we talked about universal statement. For everything, for everybody, something is true. Now we want to take the opposite of it. We want to take a negation. And for that we need a new symbol. And that symbol will stand for some. Okay, so what is that thing, the existential quantifier, other than it's the opposite of universal quantifier? So it's if universal quantifier was written as upside down A for all, existential quantifier is written as mirror image of the letter E for exists. And usually you use the word exists when you read a formula with existential quantifier, like there exists an x such that f of x is true. And the formula that exists x such as f of x is true when there is at least one value of x in that set S for which the formula evaluates to true. That value is called the witness. So witness is kind of like counterexample, but the opposite. You're trying to prove that something is true rather than prove something that's false. But actually, a counterexample to a statement is a witness to its negation, vice versa. So here's an example. If you want to say, no, it's not true that for all x, f of x, it's the same as saying, well, here is x for which f of x is false. So you try to find a counterexample for all x, f of x, and you find it by finding a witness for exists x, not f of x. So let's do some examples. Let's write down a formula for there exists an even prime number. Say our domain is integers. Well, it has to be numbers, and we usually talk about even and prime for integers. And we have predicates even and prime. So here's our formula. There exists an x such that both even of x and prime of x. Again, notice that once we have our predicates, we could treat them sort of the same way as we treated propositions. There are some things that are true or false, and we could use and, or, not, and so on to connect them. So this particular sentence is true because there is a number 2, which is our witness, which is both even and prime. Let's try another one. There is some number between 0 and 1. Let's take as our domain to be real numbers now, and let's take a predicate to be less than, strictly less than. Now the formula that encodes the sentence says there is a real number x such that 0 is less than x and x is less than 1. Is this true? Yes, because we set the domain to be real numbers, so we have a ton of real numbers between 0 and 1, like 1/2, 0.777, and so on and so forth. If I would write the same formula but with a domain of integers, this same formula would be false. Let's try another example. So when we talk about numbers being divisible, we could define what it means to be divisible like this. A number n is divisible by a number m if there is an integer which gives n when you multiply that integer by m. So for example, n is divisible by 6 is divisible by 3 because there is a number 2 that you could multiply by 3 to get 6. So here is a formula. There exists z, n equals m times z. And notice that here n and m are free variables. So we could substitute anything we want there, and depending on what n and m are, sometimes it will be true and sometimes it will be false. So for example, if n is 6 and m is 3, this is true, and z equals 2 is a witness. But when n equals 3 and m equals 2, because we are talking about integers, there is no such z. So the sentence will be false. So say one more, n and m in this formula are free variables. There is no quantifier, and we could set them whichever way we want, but we wouldn't know whether the formula is true or not until we agree on what n and m are, whereas z is bound by the quantifier. We cannot really set it to anything at will. We could say, well, yes, the formula is true and here is a witness, but it's not like we could say, okay, let's set z equal to 3 and see what happens. Okay, so let's say a little bit more formally, just like we did for universal quantifiers, what it means for a quantifier, existential quantifier formula to be true. So a formula exists x such that f of x is true, as we said, when f of a is true for some a in the set S. Like I'm teaching some course right now. Well, that's true because I'm teaching COMP1002. COMP1002 is a witness of the truth of I'm teaching some course right now. And if you remember, for universal quantifiers, we say that this is the same as taking an OR over all elements of the domain, over all elements of S. F is true with the first one, F is true with the second one, and so on and so forth. Except with the end, we wanted it to be true everywhere, so we had to put an end with a universal quantifier. Here, because we just need it to be true in one place, we put an OR. So there exists x in S f of x is equivalent to saying either f of the first element of S is true, or f of the second, or f of the third, and so on and so forth. If one of them is true, then the whole thing is true. Showing that an existentially quantified statement is false, however, is a lot harder because you will need to show a universal statement. Now we are going backward. We will need to show that no matter what element of S you pick, F will not be true on that element. So how do we translate between English and logic? As always, translating from English is the hardest part because English is ambiguous and logic tends to be much more clean and precise. For universal quantifier, usually if you have a sentence with the word every, all, each, any, then this word indicates that you will use a universal quantifier. Every day it's foggy. Each number is divisible by 1. Also, none, nobody, nothing, and so on translate as universal quantifier because they mean that for everything, something does not happen. Nobody works on Sundays. Everybody does not work on Sundays. So none is not a negation of every. Negation of every is some. None is just as universal as every. Okay, so which words would we use for existential quantifier? The word some is probably the most indicative. Some students got 100% on the first lab. That means that there is at least one student who got 100% on the first lab. In mathematics, people sometimes just write there exists. There exists a prime number greater than 100, something like this. Well, this is an obvious indication. There exists translates as existential. English has those little words that some other languages don't have that sometimes may also indicate quantifier, like an A. When you say there is a student, or a student got 100% on the first lab, even though that little a is tiny, and I wouldn't know how to translate it in a lot of other languages, that a in English would still indicate that it is an existential quantifier. But as you know, English is more confusing than logic. And there is one word, any, that can mean, well, any. Here is an example. Any can have the meaning of existential quantifier. Like if I say, can I have any piece of that pie? I'm not asking for every piece of the pie. I'm just asking for some piece. But if I say, any student in my class knows this, well, then the idea is that every single one of you know it. Here is another pair of very, very similar sentences with completely different meaning of the word any. If I say, any student can get an A in this class, I mean every single one of you can get an A in this class. If I'm scratching my head and saying, would any student get an A, I want at least one of you to get it.